Hi everyone, I just wanted to put together a short little review to summarize some of the topics we've gone over to help you prepare for exam 1. So the first thing I wanted to mention is, first of all, this video is going to be more just a general overview with theory rather than examples. There are a couple very short examples, but it's mainly just to overview everything. So, getting into it. I want to start by talking about the difference between power and energy signals. So, I'll explain it first with math, I guess. So, if you recall, these are the formulas we use for power and energy. And so, with energy, it's positively correlated with the area under a signal. And so that gives us an idea of the strength of the signal. And that makes sense. The unit for that is going to be joules, and for power, it's going to be basically the energy divided by the fundamental period. And now, the one thing I want to mention about this is this is more appropriate for signals that are repeating. Like, for example, like a continuous sine wave. It doesn't really make sense to do the energy because the energy is basically going to be infinite if it's going to continuously repeat. So we need to do the power because it's just more appropriate for those signals. So that's why we call the repeating signals power signals, and just sort of pulses or non-repeating signals as energy signals. And the equations for this make sense because since the unit for power is watts, watts is also equal to joules per second. And so if we divide the energy by the period, then that's going to give us sort of an average amount of energy per period or per seconds that the signal is omitting. Okay, so here is a little example to illustrate that. So we've got two signals, one is energy and one is power signal, and they're basically the same signal, just one is repeating. And so I notated that with the sigma notation, and I just wanted to mention that this is a nice way of representing a power signal because so the coefficient here is going to be the period, basically. But if you break it down into each of the individual terms, so like if n equals 0 here, then that's going to give us a pulse that looks like this. If n equals 1, it's going to give us the pulse shifted over here, and then so on and so forth. So it's a very short, and if we add them all together, then it's going to be like a continuous power signal. So this is just a nice short way of representing that. And so you saw that in the homework already. So hopefully you're familiar with it. Okay, so now I calculated the energy over here for the energy signal, which ended up equaling 1. I set it up by just saying, the function is equal to 1 on the boundary from 0 to 1. So that's how I set up my integral. And I did a very similar thing here, noticing that the period was 2. So, another thing I wanted to mention is sometimes some of you guys were having trouble finding the period. I know that it's tempting to say that it's 1 because that's like how long the pulse is, but you also have to account for where it's like resting, because if I just had like this signal and said the period was 1, that means every 1 second it's going to repeat. So if this signal had a period of 1, then it would just look like a straight line. So what I want you guys to do if you're having trouble finding the period is put your finger at 0 and then look at that point and then find the first point where it comes back to that. So that would be 2. So period here is 2. That's just a visual way of finding the period. But anyway, so going through with the integration, I get 1/2, and if I wanted to shortcut this and not redo the integration altogether, I could have just observed like, well, hey, this signal x of t is a repeating version of g of t, and I have the energy for that already, so I'm just going to take the energy divided by the period, which is 1/2. And this answer also makes sense to me because it's like, well, if I have a signal that is 1/2 the time and 0 the other half of the time, it would make sense to me that like sort of the average energy dissipated by it would be 1/2. So that's that example. And okay, so next let's get into Fourier transforms and Fourier series. So these two are built on the same principle that any signal can be separated into a bunch of sines and cosines. And so, you might be asking yourself, why is this helpful? Like, why am I doing all this integration in calculus? It's just math. Well, this is especially Fourier transforms. Fourier transforms are one of the most principal concepts in signal analysis. You just can't go without it. Of course, when you get in signal analysis, computer is going to do the math for you, but still, you should understand its importance. So, I just want to show you a little example of this. So, I am at a research group in UCF where we record the electrical and mechanical signals in a muscle. So I do a lot of the analysis in MATLAB, and so I just want to show you a little example of where Fourier transform came in handy for me. So this first signal right here, this is just straight from the recording, nothing done to it at all. So before I start my analysis on this, I was looking at it and I said, well, okay, so first off, this is where the actual contraction is, obviously, and then this is like the resting point. So I looked at this and I said, wow, this we call it the baseline noise, is very loud. There's a lot of signal there, and that's not very good when it comes to the signal analysis, because if I did no pre-processing, no filtering to get rid of this noise before I start, it's going to affect it in a very bad way. Like if I looked at the RMS for this, which is kind of similar to like the power of the signal, then it's going to show that the signal is just, there's like muscle contraction and there's strength over here when there shouldn't be, because that's when the muscle is resting. So what I did is, well, when I was looking at this, I zoomed in to here, and when it's zoomed in, it looks like a pure sine wave, basically. So I said, like let me do a Fourier transform just on this part, not including here, but just this part, and I could figure out what frequency that is. So I did the Fourier transform, and I saw that it was all concentrated at 60 hertz. So I continued on with methods to getting rid of the noise. One of it included filtering, so I was able to do like a narrow bandpass filter to get a signal for the noise, and to do that I needed to know what cutoff frequencies to use, and I judged that based on the Fourier transform of the noise. So now you can see it became corrected. It's much nicer, and I couldn't do that without knowing the frequency of the noise, so I needed a Fourier transform for that. Okay, so now going on into the math. These are just the equations you're going to use. If you know how to set up your equations for like power and energy and know how to break it up and break up the boundaries, then it's basically the same thing, just plug and chug, but you're going to have to split it up into multiple integrals usually. And one thing I just want to mention is that sometimes in frequency domain we use hertz, which we use the variable f for, or we use radians, which we'll use omega for. So if the test is multiple choice and you're seeing omegas in the answer choices, just make things easier, go with these equations. if you don't, don't fret. Hertz and radians are proportional, so you should be able to convert still, but it's just gonna, you might make a mistake, so just save yourself the headache. Go with whichever equation is more appropriate for the answer choices. Okay, and so now this brings up the Euler identities. So one thing I saw you guys were having issues with was you would go through and do this Fourier transform, and now you've got a bunch of exponential functions in your answer, and all the answer choices are sines and cosines. So you have to know the Euler identities so you could convert between the two. And so ideally, we usually are going to use these first two identities because, it's going to make your answer shorter and more compact and easy to read. This, you can use it, but it makes your answer larger and harder to read. So, just this is how you could get it between the two trig and exponential functions. So I have a little example here because, so usually you won't immediately see that you can do a Euler identity. Usually you need to do a little bit of algebra to manipulate it first. So this is actually an example from your homework that you guys just turned in. So I set it up. I know that the answer was in radians, so I used the formula using omega. And so plugging it in, I know from 0 to 1, my function is just equal to 1. And then from 1 to 2, it's equal to -1. So I set it up, continued on with the integration, and then I get to here. Now technically, this answer is not wrong. So if it were free response, you're good to go here. But if your professor wants it in trig functions, then you gotta continue. Or if the answer choices are in trig functions, then you gotta continue and do a Euler identity. So right off the spot, I guess I'm just gonna walk through what my reasoning would be if I were given this problem. So looking at the pairs, I know that this term and this term will not combine into a Euler identity because the coefficients are different. So this one it's 2 and this one it's 1. So they're never going to fit in one of those nice Euler identities. But these two, I could see if I could make them work into a Euler identity. So I factored out e to the negative j omega. And so this is what I got. And now I look at them and I say, oh, okay, these two look like they could be a pair, and maybe I could group them. So next I observe that they are added together. So I know it's not going to be sine, it's going to be cosine I'm going to use. So looking at the Euler identity for cosine, I look at it and I say, oh, well, I don't have it divided by 2, but that's an easy fix. I could just bring it over to the other side. So I substitute in 2 cosine omega here. And then after this, I could just factor out the 2, and this is the final answer. So I know in the beginning, the first couple problems, it seems like, how am I supposed to know that? How am I supposed to know to factor out e to the negative j omega? But after doing a few of these, you'll start finding and recognizing patterns where you'll know when to use those substitutions, and it's very repetitive. After a while, you start noticing patterns. So anyways, okay, so continuing on to Fourier series, we have 3 types. So they're all going to be for power signals that are repeating. There's just 3 different ways of writing them. Sometimes we want it in the trig form, sometimes we want it in compact form, and sometimes we want it in exponential form. So the trigonometric Fourier series is what you're already familiar with from linear circuits 2. it's got sines and cosines with your coefficients being an, bn, and a naught. So one thing that might make your math a little bit easier is just before actually doing the math, look at your signal and assess if it's an even function or an odd function, because if it's an even function, you know it's only going to be made of cosines because cosine is an even function. There cannot be any sines in an even function because sine is an odd function. And in the end of the day, all of these sines and cosines add up to make one signal. So, you know, if it's an even function, you know that there's going to be no sine terms. If it's an odd function, there's going to be no cosine terms. And one thing I wanted to note is that the subscript 0, so A naught or C naught or D naught, they're all the same thing, you know, A naught is equal to C naught is equal to D naught. And all it is basically is the average value of the signal over a period. So how that translates to, I guess, more engineering terminology is it's the DC offset of the signal. So this is one area where you could easily sort of fact check yourself with your math. And like, let's say I have like just like a square wave like this. I could easily see that this signal is centered at 0. So I know that once I go through my integration, I should get A naught is equal to 0. If I don't, something is wrong. So that's one area where you could easily check your math during your exam. Okay, so these are the formulas. Continuing on, so compact Fourier series is very similar to the trig Fourier series. It's just that, so since cosine is the same as sine, just with a phase shift, we could put those two together and have a just one term, and there's going to be added theta or shift. So these are the formulas to go from trig to compact, and this is going to be your final form for it. So, oh, that's another thing I wanted to mention. So sometimes you guys seemed a little bit confused with calculating the coefficients and actually representing the Fourier series. So remember that the Fourier series, it's always going to have some summation in there. So, because it's a sum of all these different frequency components. So, I saw that especially with the exponential Fourier series. A lot of you guys would calculate dn and say like, oh, this is it, this is the Fourier series. But no, that is just the general equation to get the coefficients for the Fourier series. The actual Fourier series is going to be your signal, or g of t, or whatever it is equal to some kind of summation. And so make sure that at the end of it all, once you calculate your coefficients, you plug it back into that form. So anyways, oh, and one thing I wanted to mention, so I guess let's go on to the exponential Fourier series. So don't confuse the magnitude of dn with dn. So magnitude is just going to be like the coefficient, and then dn is going to be the coefficient plus your exponential term. So I remember back when I was taking this course, I got a little bit confused by that, but that's the difference. So the exponential Fourier series, it could be represented in two different notations. It's saying the same thing, it's just a different notation. Okay, continuing on. So this is how you could go from compact to exponential, in case you ever need that. So yeah, so like I was saying earlier with the difference between dn and and the magnitude of dn. This section is just the magnitude of dn, but the whole term is dn. Okay, so going on. Okay, so correlation coefficients. So this is the general formula. Hopefully you guys have worked with that by now. And so one thing I want to mention is that it is always going to be some value between -1 and 1. If you get anything outside that, your answer is wrong. So how I like to think about correlation coefficients, or like how I like to make sense of it, I guess, is I think of it as like the percentage of similarity. I know these aren't in percentages, but like if 1 is 100% and then -1 is -100%. So that's how I think of it. So if I have two signals that are the same, like g of t and x of t, then I know that the correlation coefficient is 1 because 100% of it is the same. If I have like two signals and g of t is equal to negative x of t, so they're basically the same signal, just negative times -1 for one of them, or they're the opposite, then I know that they are 100% like not the same, or 100% dissimilar. And then if they have like no similarities whatsoever, then they have a correlation coefficient of 0, or they are orthogonal. And sometimes we like to use the analogy where correlation coefficient is 1 is their best friends, if it's -1 they're enemies, and if they're 0 they are strangers. So that's one way you could think of it. So now going on to why would this be helpful? Why would I want this value to show how similar they are? Well, let's say we have a bunch of different signals to choose from. We are going to make some kind of transmission, and we have all these signals to choose from. Oh, this is 1, this is 1/2, this is -1. And all these are on t. And then 1, 1, 1, and then 1. So if let's say I want to do some kind of binary transmission, so I'm going to be doing 1s and 0s, or whatever you want to think of. And I have all these signals to choose from to represent 1 and 0. So I would want the ones that are most dissimilar, or the correlation coefficient is equal to -1, because that way that means that the receiver is the least likely to confuse the two. If they're like pretty similar, then that's a bad choice. You don't want to do those two pulses, or those two signals, because then the receiver is going to keep mixing them up. You might not be able to transcribe whatever the signal is trying to send. So if I look at these, I know that the two that are opposite, or with the correlation coefficient of -1, are these two. And that makes sense because a lot of times when we do a binary transmission, we end up having some kind of like square wave. So that's like a little example of why this might be useful to know. So that's all I have for this little review. I hope that this was helpful. If you guys have any more questions, feel free to pop into my office hours or send me a message on Canvas. Thank you.